Hello guys, so welcome back to this channel. Okay, so in this video I'll be teaching you guys capacitor, okay, which is a particular subject in which is a particular topic in PHY102. Okay, so these are all the outlines you need to know about capacitor. So these are everything we'll be treating in this video, okay, regarding capacitor. Okay, so let's start with the very first part, which is introduction to capacitor. What is a capacitor? What do you understand by the word capacitor? Okay, so now what is a capacitor? Now, in simple terms, a capacitor is a device that stores charge. Okay, so that is in simple terms a device that does what? It's a device that stores charge. Okay. Yes, a capacitor is a device that stores charge. Now let's talk about the structure of or the component of a capacitor. Okay, so now a capacitor is made up of two metal plates. Okay, so a capacitor is made up of what? Two metal plates. Okay, so this can be the positive metal plate, the positive, this can be this is the positive plate, and this is what? This is negative plate. Okay, so a capacitor is made up of two metal plates, the positive plate, negative plate, separated by what? Separated by what we know as a dielectric. Okay, a dielectric. So these are the components of the capacitor. Capacitor is made up of two metal plates, a positive plate, a negative plate. These two plates are separated by what? By a dielectric. Now, what is a dielectric? Dielectric is an insulating material. An insulating material is a material that does not conduct electricity. Okay, so this is how a capacitor looks like. Capacitor is made up of two plates separated by what? By a dielectric. Now you may ask, what is the function of now why is it that the two plates in a capacitor is separated by a dielectric? Now now remember, a dielectric is an insulating material. That is a material that does not conduct electricity, right? Yes, a dielectric can be air, can be paper, okay, can be paper, it can be plastic. Yes, can be plastic, can be a glass. Okay. So and many others. It can even be a ceramic. Okay. So important thing you need to know is that the dielectric is an insulating material. Now the function of a dielectric in a capacitor is to prevent charge from moving from one place to the other plate directly. I don't know if you understand, because a dielectric is an insulating material, so it prevents charge to move directly from one plate to the next plate. So that is it. So that is the function of a dielectric in a capacitor. Apart from that one, it helps to increase capacitance. Okay, so let me not go far. All right. So the important thing you need to take note of under a capacitor is that it is a device that does or that stores charge. Okay, that is number one. Then it is made up of two metallic plates separated by what? A dielectric. Remember, the two metallic plates, one is a positive plate, the other one is a negative plate. Okay, then these two metallic plates, they are separated by what? A dielectric. Remember, a dielectric are what? Are insulating materials. Can be air, can be paper, can be plastic, it can be glass, it can be what? Ceramics. Okay, yeah, so it prevents current from moving directly from one plate to the other plate. So it separates the two plates. Okay, yes. Apart from that one, a capacitor is represented by the symbol like this. Okay, so this is the symbol of a capacitor. So this is how a capacitor is represented. All right, so now let's move to the next part, the types of a capacitor. So there are different types of capacitor, and we have the leading jar capacitor. Okay, we have the variable capacitor, we have the fixed capacitor, then we have the electrolytic capacitor. Okay, so there are different types of capacitor: leading jar capacitor, variable capacitor, fixed capacitor, electrolytic capacitor. Okay, so I'll give you guys some important things you need to know. You need to know under this type of capacitor. I will start with the variable capacitor. Now, a variable capacitor, these are capacitors that have variable capacitance. Okay, so they have variable capacitance. Capacitance. Don't worry, I will tell you guys the meaning of capacitance. Okay, soon. So that is our next, and that's where we are going next. Okay, so a variable capacitor, okay, is a capacitor that has a variable capacitance. This capacitor, they are adjustable. Okay, yes. The another thing you need to know of under variable capacitor is that these capacitor, they are used in radio tuning. Okay, they are used in what? In radio tuning. Okay, they are used in radio tuning. For this reason, a variable capacitor, they are also called tuning capacitor. Okay, they are also called tuning capacitor. Okay, so the important thing you need to take note of under variable capacitor is that the variable capacitor, there are capacitor that have variable capacitance. They are used in radio tuning. They are also called tuning capacitor, and also there are also capacitor that there are capacitor in which their capacitance can be adjusted. Okay, yes. Then the opposite is now fixed. A fixed capacitor, these are capacitor that have what? They have a fixed capacitance. Okay, they have fixed capacitance. Okay, that is, so fixed capacitor, these are capacitor that have fixed capacitance. That means that they have a constant capacitance. Okay, so yes, so that is the important thing about that fixed. Then electrolytic, the important thing you need to take to you need to know under electrolytic capacitor is that this capacitor, they have the largest capacitance. They have a very large capacitance. Okay, then leading jar, this capacitor, they are made up of outer and inner coat. Okay, and a metallic rod. Okay, so that is all about so that is all you need to know of about types of capacity, the different types of capacitors. Okay, so now let's move to the capacitance of a capacitor. Okay, so the capacitance of a capacitor. Okay, so now what is the capacitance of a capacitor? Remember, a capacitor is what? Is a device that does what? That stores charge, right? Then what is the capacitance? Okay, capacitance of a capacitor. Okay, of a capacitor. Now, the capacitance of a capacitor is the ability, okay, is the ability of a capacitor to store charge, to store charge. Okay, so that is it. The ability of a capacitor to store charge is known as the capacitance of a capacitor, or capacitance of a capacitor. You can just say, okay, is presented by C. Okay, so this is the capacitance of capacitor. You can just say the capacitance of a capacitor is the ratio of the charge stored by that capacitor over the voltage between the two plates. Okay, so capacitance of a capacitor is the ability of the capacitor to store charge, or it is the ratio of the charge stored by that capacitor. Okay, you can say, okay, ratio of this, yeah, the ratio of the charge stored by that capacitor to the voltage between the two plates, or you can say it is the charge stored by the capacitance of the capacitor is the charge stored by a capacitor per unit volt. So that per unit voltage, so it's the same thing. Okay, so this is the formula for the capacitance of the capacitor. Okay, so it tells us now. Let's say, for example, okay, now follow me. Now this quantity here is known as what? It's known as capacitance of what? Of a capacitor, right? It is the ability of the capacitor to store charge, or it is the charge stored by a capacitor per unit voltage, right? The charge stored by a capacitor per unit what? The volt, right? Yes. Now, what is the SI unit of this quantity? The SI unit of this quantity is known as what? It's known as farad. Okay, we know the SI unit of charge. Charge is coulomb, right? Coulomb. Then we know for volt, voltage is still what? Is still volt, right? Yes. So farad is the SI unit for capacitance. Okay. Yes. So then now, and let's dive deeper. Capacitance of capacitor is equal to charge stored by that capacitor per unit voltage, or the ability of a capacitor to store charge. Now, if a capacitor has a capacitance of 2 farad, remember the SI unit of capacitance is farad, right? Yes. So if a capacitor has a farad, let's say has a capacitance of 2 farad, has a capacitance of 2 farad. What does this mean? It means that, remember, let's according to the formula, it means that the capacitor was able to store 2 coulombs of charge and in one what? In one voltage. Now if you understand. Because if we do it, 2 divided 1 will give us what? Remember, capacitance is equal to charge over what? Over voltage, right? Yes. So if you say, if the capacitance of the capacitor is 2 farad, what does that mean? It means that the capacitor was able to store two coulombs of charge. Remember, this C is coulombs, this V is volts. Okay, so the capacitor was able to store 2 coulombs of charge in what? In one voltage. Let me understand. If it's okay, if it's 4, let's say if it's 4, let's say the capacitor is 4, it means that the capacitor was able to store what? Was able to store you can see it was able to store 4 charge in what? In 1 volt. Or because 4 divided 1 will give us 4, right? Yes. Or you can say the capacitor was able to store 8 charge in what? In 2 volts. See the same thing. 8 divided 2 give us 4, right? Yes. Or you can say it was able to store 16 coulombs of charge in what? In okay, 16 going to divide 8. Okay, in 4 volts, right? So that is just it. So it give us 4 farad, right? Yes. So this is all about capacitance and capacitor. The important thing you need to take note of here is the formula. C is equals to capacitance is equals to the charge stored by the capacitor divided by the potential difference or the voltage between the 2 plates, right? So this is the formula. The SI unit is known as what? Farad. So that is just it. Okay. Then one more thing, I'm coming. Okay, one more thing. I've told you guys earlier, when you see something like this is macro, this is pico. Okay, this is pico, this is milli. Okay, micro, pico, milli, nona, right? Micro means 10 raised power what? Minus 6. Pico means 10 raised power minus 12. Milli means 10 raised power what? Minus 3. Then nano means 10 raised power what? Minus 9. So for example, let's say for example, a capacitance is 4 microfarad. What does it mean? It means if you convert, it means that the capacitance is what? 4 times 10 raised power what? Micro is what? 10 raised power minus 6, right? Then you put your farad there, right? So know these things, okay? It's very important. All right, so now let's go to the next part. The factors affecting the factors affecting the capacitance of the capacitor. Okay, so what are the factors that affect the capacitance of the capacitor? Okay, remember this is the formula of the capacitance of the capacitor, right? Okay, so now let me tell you guys the factors that affect the capacitance of the capacitor. The factors that affect the ability of the capacitor to store charge. Okay, so one of the factors that affects the capacitance of the capacitor is one the area. Okay, is one the area of the plate. Okay, the area of the plate. Okay, the area of the plate. Two, the distance between the 2 plates. The distance between the plates. Okay, between the plates. Okay, three, the you can say the nature. Okay, the nature of the dielectric. The dielectric. or we can see the thickness of the dielectric, dielectric, okay, thickness of the dielectric, or another one, or the density, okay, or density of the dielectric, okay. So so that is number three. The another one, another thing, another factor that can affect the capacitance of the capacitor is the geometry of the plate. The geometry of the plate. Okay, so these are the factors that affect capacitor. Okay, so these are the factors that affect capacitor. The area of the plate. So now let me give you guys the formula. So the factors that affect the capacitance of capacitor. Let's start with the area. Okay, so this is the capacitance of capacitor, right? So what are the factors that affect is the area of the plate, the distance between the two plates, the nature of it, or the thickness or the density of the dielectric. Then apart from that one, the geometry of the plate. Okay, so now the area, the capacitance of a capacitor is directly proportional to what? To the area of the plate. Okay, so the larger the area. So this means that the capacitance is directly proportional to the area, right? So this means that the larger the area of the plate, the larger the area of the plate, well, the higher the what, the larger the capacitance. Okay, so that is tell you that if a capacitor has a large plate, if the plate of capacitor, if the plate of the capacitor has a large area, so that is the capacitor we has, well, we have a large capacitance. What does that mean? It means that the capacitor will store more charge. That is if the area of the plate is large. Okay, then the other one, the capacitance of the capacitor is inversely proportional to the distance between the plate. Okay, it's inversely proportional to the distance between the plates. So what does that tell you? It tells you that the higher the distance between the plates, the lower the capacitance, or the lower the distance between the plates, the higher the capacitance. So what does that tell you? It tells you that if the distance between the plate is very large, if distance between the plate is very large, capacitance, look at it, capacitance is inversely proportional to to distance. When you see something inversely proportional, it means that whatever is happening to one of that thing, the opposite will be happening to the other one. So for example, let's say if one is increasing, the other one will be decreasing. That is, I don't know if you understand. So that is one inversely proportional. Okay. So the capacitance of the capacitor is inversely proportional to what? To the distance between the plates. So that is tell you that if the distance is increasing, the capacitance will be decreasing. Or if the distance is decreasing, the capacitance will be increasing. Okay, so that is just it. So that is tell you that if the distance between the two plates is large, the capacitance will be what? Will go down, right? Will decrease, right? Now, but if the distance between the two plates is small, the capacitance will increase. So what does that tell you? What does that tell you? It tells us that if the plate distance between two plates is very close, the capacitance will be high, right? Yes. So that's just it, okay? So now move to the next one. Nature of the dielectric. Okay, nature of the dielectric. The capacitance of the capacitor is directly proportional to the dielectric, okay? Directly proportional to the dielectric. Yes. Is directly proportional. Also, when you see some things and when you see two quantities are directly proportional, it means that if one is increasing, the other one will still be increasing. Then if one is decreasing, the other one will still be decreasing. Whatsoever happened to one of them, the same thing will happen to the other. Then for inversely proportional, it might be opposite. If one is increasing, the other one will be decreasing. If for the other one is increasing, the other one will be decreasing. So it's opposite. Okay. So now, nature of a dielectric or the thickness of the dielectric. Okay, so the capacitance of the capacitor is directly proportional to the dielectric, to the nature, or you can see the density of the dielectric. Okay, now let me break it down. Remember, I told you guys that the dielectric, they are what? They are insulating materials, right? Found between the two plates of a capacitor. I told you guys that the dielectric can be air. Yes, it can be paper. It can be block. It can be glass. can be anything, okay? Like insulating thing, okay? It's not things that does not conduct electricity, okay? Now, look at it. Capacitance of capacitor is directly proportional to the dielectric, okay? To the directly proportional to the nature of the dielectric, or the density of the dielectric, or the thickness of the dielectric. So that's to tell you that if a capacitor, let's compare two different capacitors. Now, density. Now let's say, for example, let's say this is a capacitor, and the dielectric used in this capacitor is air. Okay. Then let's say this is another capacitor. Then the dielectric used in this capacitor is paper. Okay. Now, which between these two capacitors, which one we have the which one we have the highest capacitance? So which one will store more charge? It will be what? It will be this one that has a dielectric, that has paper as a dielectric. Do you know why? Because paper is denser than what? Than air. Paper is not thicker than what? Than air. I don't even understand. So paper has a larger density than air. So that is tell you that this one that has air as the dielectric, and this one that has paper as dielectric, this capacitor will store more charge. That means this capacitor will have a higher capacitance than this other one. Don't you understand? So that is tell you that capacitance of the capacitor is directly proportional to what? To the thickness or the density of the dielectric. So that's tell you that the higher the density of the dielectric, the higher the capacitance. Okay, then the lower the density of the dielectric, the lower the capacitance. Okay, yes, let's use this again. Between these two, which one the dielectric has more density, has large density, is this one, right? Paper is denser than air, right? Yes. Now let's do another one. Let's compare another one. Now let's compare block. Let's say this one has block. Let's say this one has block. This one has paper. Which of these two uh, okay, let's say this one has glass. Okay, it has glass. Okay, now which of these two capacitor we have a higher capacitance? It will be what? It will be this one, because where glass is more thicker, or glass is more denser than paper. Okay, remember, according to this, the higher the density or the thickness of the dielectric, the higher the capacitance. So that's say that the higher the ability of that capacitor to store more and more charge. So that's just it. Okay. So that is it. So now let's derive a formula from these factors that are affecting the capacitance of the capacitor. Remember, I told you guys that um, capacitance of the capacitor is directly proportional to the area of the plate, right? The larger the area, the higher the capacitance. So that is tell you that the larger the area, the more the capacitor store charge. Then I also tell you guys that the capacitance of the capacitor is inversely proportional to the distance between the two plates. So that is saying that the closer the plates are together, the higher. If the two plates are closer, if they are closer, what does that mean? So that's saying that distance between them is what? Decrease. If the two plates are far away from each other, what does that tell you? It tells you that distance between them increase, right? So in this first scenario, the distance between these two plates, they are what? The two plates are closer, so let's say that the distance between them is small, right? So what will happen with the capacitance? The capacitance will increase, right? Yes. So what about this scenario? Distance between the two plates is what? Is large. What will happen to the capacitor? The capacitance to what? To decrease, right? So that is just it. All right. So then the last one, and the capacitance of the capacitor is directly proportional to what? To the thickness of the dielectric. So if we combine everything, we arrive at a particular formula. Okay, so remember, I've given you guys one formula already. The formula I gave you guys earlier was that capacitance of the capacitor is equals to the charge stored by that capacitor divided by what? The voltage between the two plates, right? Yes. Now take note of this one formula first, then let's join this. If we join them, we have a particular formula. Okay, so capacitance is directly proportional to what? So to the area and inversely proportional to what? Inversely proportional to the distance between two plates, right? So if we remove this and place a constant there, the constant becomes, okay, I'm coming. Okay, so if we remove the proportionality sign, we introduce an equals to then a constant, right? Yes. So that constant is known as the electric constant. Okay, so E naught. So this is it. Okay, so this is the formula. So C is equals to E naught multiplied by the area divided by what? The distance. So this is the formula for the factors that affect the capacitance of a capacitor. Okay, you in this formula you find out that C is directly proportional to E naught is still directly proportional to A. Then you find out that C is inversely proportional to what? D. Right? So yes. So this is the formula for the factors that affect the capacitance of the capacitor. Okay, so the capacitance of the capacitor is equals to permittivity of free space times the area divided by what? The distance between the two plates. Okay, yes. So this is one formula, this is another formula. So if they ask you a particular question, they give you a particular question, they give you charge and they give you voltage, and they say calculate for the capacitance of the capacitor, use this formula. Then if they give you area, they give you distance, then they will not give you this one directly. Remember, I've told you guys countless times that permittivity of free space is equals to what? 8.85 times 10 raised by what? Minus 12, right? So this is the value for permittivity of free space. Okay, so that is it. Okay, so if they give you area, they give you distance, and they take a look at capacitance, use this formula. Okay, if they give capacitance, they give you distance, they say look for area, use this formula. If they give you capacitance, they give you voltage, they say look for charge, use this formula. So that is just it. Now, do you know that we can join these two formulas together? Yes, we can. Yeah, there are some certain situations where they will ask you to calculate for. They'll give you area, they'll give you area, they'll give you distance, they'll give you volts, they say calculate for charge. So which formula are we going to use? You need to join the two formula together. So that is just it. How are we going to join the two formula? It's very easy. Okay, so if you look at this first formula, capacitance is equals to what? Charge over volt. So if we take charge over volt, place it where that means so that tells that charge over volt is equals to C, right? Yes. So wherever we see C, we'll put charge over volt. So that is just it. So C here is what is charge over volt, right? It's equals to what? E naught A over what? D. So this is another formula, right? Yes. So you can use this as well. So in this one, we can use this formula when, for example, they give us volt, they give us charge, they give us distance, and they say look for what? Area. Simple. You combine them. Yeah. So that is just it. Okay. So take note of this formula, take note of this one, take note of this one. So that is just it. Okay. Yes. Now I want to tell you guys another important thing. Okay, regarding this formula. Now if you look at this formula, capacitance is equals to E naught multiplied by area over the distance, right? Yes. Now, if you look at this formula, is used when the dielectric of this particular capacitor, when the dielectric is here. Okay. Now, when the dielectric in this capacitor, when the dielectric is here, the formula we're going to use is what? Z naught. Hey, right? Yes. Okay. When the dielectric is here, or you can say when the dielectric is here. Okay. Yes. Now, but when a dielectric is a material, is a material medium like glass, paper, or block or ceramics. When it's a material, because remember you cannot touch air, right? So now when the dielectric is a material, we can no longer use this formula. We need to add something to it. Let me understand. If the dielectric is a material medium, we cannot any longer use formula. Like we need to add another thing to it. And remember in our previous class, I told you guys that um what they call it to permittivity, relative permittivity is equals to permittivity of the medium divided by what? Permittivity of free space. Right? Yes. Now if the dielectric we use is air, we use E naught here. Now, but if the dielectric is a material medium, we use EM. I don't even understand. So if we make EM subject formula here, we cross multiply. EM will be equals to what? Will be equals to relative permittivity multiplied by what? Multiplied by permittivity of free space, right? Yes. So in this place, if it's a medium, okay, now let me give you guys another formula. Therefore, in a medium, in a material medium, C will be equals to EM A over what? D. And what is EM? EM is what? Relative permittivity times what? E naught, right? So in the place of EM, we can put E arrow E naught, then times A divided by what? D. Okay, yes. So in some particular test, you will see something like this. You see something like this. K arrow is equals to Km over what? K naught. So it's still the same thing. It's actually the same thing. Okay. This means relative permittivity, permittivity of medium, permittivity of free space, permittivity of free space. So they are the same thing. Okay. So you can put K arrow K naught. So they are the same thing. Km is equals to K arrow multiplied by what? K naught. So it's the same thing. Okay. So this we use this formula when we are dealing with when the dielectric is a material medium, okay, like glass, ceramics, paper. But when it is air, we make use of this one. So yes, so in total, I've given you guys four formulas. So not four formula, I've given you guys five formulas so far. This, and this as well. So take note. Yes. So and this as well. Okay. Yes, so that is just it, okay? Yes, so that is all about factors affecting the capacitor. So taking note of these formulas and all. Now let's move to the next part, which is the connection of capacitor. Okay, so connection with capacitor. All right, so I will still give you guys some other important notes under this place. So under connection of the capacitor in a DC circuit, capacitor can be connected in two different ways. Can be connected by series arrangement and in parallel arrangement. Okay, in parallel arrangement. Okay, in parallel arrangement. So I will start with now. I will give let me show you how you know series arrangement and how you know parallel arrangement. In a series arrangement, we have something like this. Okay, we have something like this. All right, so something like this. Okay, yeah, something like this. Okay. Then in a parallel arrangement, you have something like this. You have something like this. Okay. So let's say this is the voltage. Okay. So you have something like this. Mm, all right. Okay. Okay. You have something like this. Okay. Yes. You can also have something like this. I will tell you how you will know them. Okay. Okay. So okay. All right. So you have something like this as well. Okay. So this one is voltage, okay? This one is capacitor. How do you know capacitor? I've given you guys the symbol earlier. They are the two equal plates. They are the two equal plates, they are equal. Right? The plates are equal. But if you want to know a battery or a source power, they usually have one longer this line and a smaller and a shorter one. So this is a battery or a power source. Yes, or you can say, yeah, power source that produces a volt. Okay, so this one is a capacitor. Okay, yes, capacitor. This one is a battery. Okay, or a cell. Okay, so now how will you know if this is because this one is series arrangement while this one is parallel and parallel. Now how do you know series arrangement? It's very easy. From the word series, let me just give you a simple thing to you used to know. All the capacitor, this capacitor one, this capacitor two, capacitor three. Okay, now all the capacitor they are connected by one wire. Let me use that word, by one wire. So when what is connecting them is just like they're connected by one. If you look at it, they're connected by one, right? Yes, there's no division. Now, but if you look at this other one, let's say C1, this is C2, this is C3. Now, okay, yeah, okay, yes. But one, okay. If you see this other one, you find out that this is parallel because if you look at it very well. Let's say this one, this is going, it's going like this, then it's going like this, going like this. Find out that it's now divide, right? When there is a division, whenever you see division, Remember, it is when you say, okay, these things they all divide. You know, okay, this is this, you know that they are parallel. Okay, but for series, they just have there's this. Do you see anything that you see anywhere these things these terminals divide? No, you didn't see anywhere those these things divide. There's no division here. So this is series arrangement. Okay, but in a parallel arrangement, there's only division. There must be division. You look at this one here. You see, look at it here. At this point, divide. Go here. See divide, right? So this capacitor, they are all parallel to each other. Look at this one. They are parallel too. Look at it. Okay, so you go to this place, you divide, right? Divide, right? Yes. So these three capacitors they are what parallel. These three capacitors they are what parallel. Why this one they are in series? Okay, now let me restructure another one. Okay, so now what if we have something like this? What if we have something like this? Okay, okay, something like this. Okay, now all right, so is this one parallel series? It's this series. Look at it. Do you see anywhere the wire divide? No, there's no where there's no division here. It just continues. Okay, it just continues. Right? Yes. Okay, now where if we now have something like this? Look, oh, where we now have something like this? Okay, now something like this. Now, let me tell you guys something. Look, if you have one something like this, this is a both series arrangement and parallel arrangement. Let me tell you, do you know why? Because if you look at this first part, let's say the C1, C2, C3, capacitor 4, capacitor 5, capacitor 6, capacitor 7, capacitor 8, capacitor 9. Now if you look at it very well, let me tell you guys, if you look at this one, look at it. These all series, right? These all series, right? They are connected by just one this thing, right? So this is just series, right? Series. So in this scenario, these theory, they are what series to each other, right? Same thing goes here. These ones too, they are all connected by the same thing, right? So these three, they are all series together. Same goes here, they are connected by one this thing, right? So they are still series to each other, right? Yes. Now these three they are in series, they are in series. Now to each other, right? One capacitor 1, 2, 3 they are in series, 4, 5, 6 in series, 7, 8, 9 in series, right? Yes. Now, but what about to each other? Like from what about this one and this? Are they in series? No, they're in what they're in parallel. Look at it. Look at it. Okay, the wire okay, all of them here are in series, and wire is going, then wire now divide, right? So it's not divide. So to tell you that these ones they are parallel to this to show that these are all parallel, right? Yes. So that is just it. Okay, they are all parallel to each other. Yes, this one they are is parallel to this, parallel to this. Look at it. It's coming like this. Then you see where they divide. You see, must see division. Where you see division, no, you know that they are what parallel. They are parallel. Look at this one. There's no division here, right? So tells you that this all of them here they are parallel to it. They are series. They are in series, right? Then we continue. Find out that they not divide. So now tell you that this one's in parallel to this one yeah, and still parallel to this, right? Now, if you look at it, there's no division here. So it tell you that all of them here are in series to each other. There's no division here. So tell you that all of them here are in series to each other, right? Yes. But with these three, with these ones, they are parallel because of course look at this where they divide, right? So they are parallel. So that is just so that is how you know parallel and series. Okay, series we never see division. Okay, look at this place. Do you see division here? No. Then you continue. It's not divide. So oh yeah, is now this is not parallel. But within these guys, they are all series. They are series. Then if we let's say we take this one, this full as component one. Okay, component. Let's call this one A, we call this guys B, call this guys C. So A, B, C, they are parallel to each other, right? Yes, they are parallel. Then what about C2, C1, C2, C3? They are all in series. C4, C5, C6, they are in series together to each other. C7, 8, 9, they are in series to each other. Now, but what now C4, C5, C6, and C3, C2, C1 are they in series to each other? No, they are what? They are in parallel. This component is parallel to this one. Same goes to this one. This component is parallel to this one, parallel to this. So that is just it, okay? So that's all about parallel. We are not done yet to so that's all about parallel and series. So the reason why I gave you guys that example is because they might ask it, okay, so I just want you guys to be versatile, okay? So when you see something like this, okay, you see something like this, I'm coming, something like this, okay, this is parallel. This series, right? There's no breaking point, there's no division. Now, but what about you see something like this? Okay, when you see something like this, they are what? They are parallel because why? Look at it, there's only division, right? Yes. So parallel series, okay, so now, let me give you guys some theories behind these guys. Okay, so now take note that in parallel is very very important. Like please and please, is very very important. Take note. In parallel arrangement, the voltage. Okay, let's okay, this is parallel, right? I'm coming. This is parallel, right? Yes, this is parallel. Okay, I'm coming. Okay, let's say this is a volt. This is parallel, right? See, okay. Now let's say this is 2 volts, for example. Now, let's say this battery is producing 2 volts. Okay. So now, in this is a parallel arrangement, right? How do you know a parallel? I've already told you guys. See that division. Now, in this type of now, please take me in parallel arrangement. In parallel arrangement, the voltage in each of the capacitor is the same. Okay, that is in parallel. Please don't forget is your voltage, or you can say PD. Okay, voltage, or remember voltage is something as potential difference, is what is the same. Okay, so let me tell you that, for example, if they want to trick you, I'll just give you some, I give you many questions. I'll say this capacitor has a charge of this one has charge of this one has, if that's what is the volt stored in, what is the voltage in this capacitor? It's 3, it's 2. In this one it's 2. In this one is 2, because where they are connected what in parallel. In parallel, the voltage or the potential difference in the capacitors, they are the same. Then the charge is now different. Okay, so potential difference of voltage is the same in parallel connection, and why the charge is different. Okay, charge is different. Remember, charge is represented by Q, voltage V. So the charge stored by this one is different from the charge stored by this one. The charge stored by this one is different from this. So important thing you need to take note of is that in parallel arrangement, the voltage is the same in each of the capacitor. The voltage is the same. Then the charge stored by each of the capacitor is different. Okay. Then let's go to series. In series, it's not the opposite. Okay. So in series, in series connection coming. Okay, so let's say this is series connection. Okay, so in series connection, the voltage or potential difference is what is different. Is different. Okay, yes. So this is that this capacitor. Okay, so this is that in parallel in series arrangement, the capacitor have different voltage, right? The voltage in this one, they are all different, but the charge is what the same. Okay, so voltage is different in series arrangement, while the charge, we know that charge is Q, right? Charge is what the same. The charge stored by the capacitor is the same. So in series arrangement, all of them they still the same charge, okay, but the voltage is different in each of them, okay. Then in parallel arrangement, the voltage is the same, all of them are the same voltage, but the charge that they store is different. So this is important thing to know. Then another last part under the series and parallel arrangement, the formula, okay. So let me give you as a formula. All right. So now if they in series arrangement, okay, in series arrangement, okay, in series arrangement, to calculate the total capacitance of the capacitor. Let's say, for example, let's say these are the capacitance. Okay, so this is C1, C2, C3. This is in series arrangement, right? Yes. So if they ask you to calculate for the total capacitance of the three capacitor, to calculate the total capacitance, we use this formula. In series, we use something like this: 1 over, to calculate the total, is 1 over this is equals to 1 over C1 plus 1 over C2 plus 1 over what C3. Okay, so this is what in series arrangement. Then in parallel arrangement, to calculate for the total capacitance, just straightforward. C1 plus C2 plus C3. Okay, okay, I'm coming. This is okay. This is series arrangement. This is parallel arrangement, right? So in parallel, this is parallel arrangement. So in parallel arrangement, we will only for the total capacitance. We do this like this. Okay, total capacitance is equals to capacitance of the first capacitor plus capacitance of the second capacitor plus capacitance of the third capacitor. So it's just straight addition straight. Then this other one under series to now be 1 over the capacitance of the first capacitor plus 1 over the other one plus 1 over the other one. Okay, so now we get what the total. Okay, so I want to tell you guys something. Okay, now let's say you do everything, you get let's say 10 over 20, and this is not your final answer. This is not your final answer. Remember, we're looking for CT. That is in series arrangement. I just want to tell you guys. So when you get something, we have something like this. This is not your final answer. We are looking for CT, not 1 over CT. So what are you going to do? You cross multiply. Cross multiply. 20 times 1 give us 20. 10 times CT will give us 10 CT, right? Then divide both side by 10, right? So you can cancel this. So your total capacitance now be 2, something like that. I don't know if you understand. So if you do, let's say, yeah, let's just, so now let's say, for example, we have something like this. And okay, we have, this one is 1, this one is also 1, this one is 1, this one is 1, right? So, for example, our total capacitance should be 1 to 10. I'm coming. Okay, so I think it's 1, okay. I think it will be 3 over 1, something like that, right? Yes. Now this will not be your final answer. I don't even understand, because we are not looking for 1 over this. We are looking for just the total capacitance, not the 1 over the total capacitance. I don't even understand. So when we do something like we have 3 over 1, right? Is this the total capacitance? No. We cross multiply. I'm just telling you guys that is in series arrangement, unlike in parallel arrangement. In parallel arrangement, you just add direct, right? Yes. In series arrangement, when you do everything, you arrive at like this. We are not looking for the 1 over the total capacitance. We're looking for just the total capacitance. So what are you going to do? Cross multiply. 1 times 1 give us 1. Then this one give us this thing, right? So divide by 3. So the total capacitance in this scenario will be what? 1 over 3. So be careful. All right. So that's just it. All right. So that is all about connection of capacitor. Okay, I've given you guys the formula. In series arrangement, do something like this. Okay, it does not mean that it must end in C3. If there are 5 capacitance, you will C1 plus C2 plus C3 plus C4 plus C5. Okay, so this for parallel arrangement. Then why this one is for what? For series arrangement. Okay, for series arrangement. Okay, then last part, energy stored in the capacitor. So now the energy stored in the capacitor, let me get the formula. Okay, so remember this one is for series, for parallel. This one for parallel. Now the energy stored in the capacitor is very easy. Okay, so energy stored in the capacitor. All right, so the energy stored in the capacitor. Remember, okay, is equals to half CV square. Okay, so just know this one. If you know this one, you can get the rest. Okay, so there are theory. So the energy stored in the capacitor is equals to half CV square. Okay, I told you guys, if you know this one, you can drive the rest. Okay, so let's get the other. There are three. We have gotten one. Let's do the other 2. Now, this is capacitance. Right? Remember, capacitance is what? Capacitance is charge over what? V. So if we put charge over V in place of this place, we have something like this. We have in place of C, we have charge over V, then times V square, right? This V will cancel this V. We'll be left with 1 V. Therefore, energy will now be half QV. So this is another formula. Okay. Yes, this is one formula. Then let's get the other last one. Okay. So the last one, make use of this from this formula. Let's make V stand alone. Remember, for this first one, remember C is equal to Q over V. When we replace C with Q over V, right? So we get this. Now in this other one, to get the third one, we need to replace V. Now to make this subject formula here, we have something like this. we have something like this, right? Make this other formula here. So if we, in place of V, we put charge over over capacitance. We have something like this. E is equals to half C. In place of V, we put charge over capacitance, right? So V is okay. So charge over capacitance. Remember, V carries square, right? Yes. So this one will cancel this. We'll be left with one C. Remember, the square affects C. So E will now be equals to half Q square over C. So this is another formula. Okay. So let me. So this is one formula, another formula there, and this one, other one, half charge, the square of charge over what C, or the sentence, C sentence, the square of the charge over what 2C. So that's just it. So these are the energy. So these are the energy stored in a capacitor. Okay, so I'm taking note of this one, taking note of this one, taking note of this one. So the energy stored in the capacitor, you can see it like this, or you can see this one as what, half Q square over what C. So yes, so the same thing. So these are the energy. So these are the energy stored. This formula can wait for the energy stored in the capacitor. Okay, so the next we move to the some important calculations. Yeah, we move to questions and answer. Okay, yeah, move to questions and answer.